So just to recap what we've been doing in this course so far. In the last lecture, Professor Amarnath had talked to you about electric motors. And he was particularly talking about the DC variety and permanent magnet type of motor. After introducing you to the basic characteristics, in the last lecture he talked about the importance of looking at the temperature. He also talked about the importance of looking at the bearing reaction forces, because these are often neglected because we are looking at the requirement of the positioning and the speed and the torques. Many times we overlook important considerations like bearing forces. Then also how fast you want to move things, so the frequency response. Okay, then he moved on to talking about stepper motors. And also to some introduction to hydraulic and pneumatic actuators. Recall that from the beginning of the course you have learnt about basically different type of applications robots are used in, and the basics of the robotics, which means you talk about the configuration of robots, degrees of freedom of robots, reach, workspace, accuracy, precision, and then the last topic that was covered was about actuators. So when we talk about actuators, we are talking about something that is like muscles, and if you have powerful muscles but if you're clumsy, then it doesn't do you cannot do fine job. So that brings us to our next topic that I'm going to start covering, which is dealing with sensors and controllers, right? So it's a issue of brawn, which is the actuator, versus brain. So brain is responsible for sensing and using the sensory feedback to make the actuators do something that is going to be will respond to the environment, which will do something that is desirable. Now, as far as robotics is concerned, we divide the sensors into two different type of sensors. Primarily, they will be called internal state sensors and external state sensors. Okay, these are sensors we are talking about. We will talk about controllers after that. What do we mean by internal state sensors? These are sensors which help us in the basic movement of the robot. So basic movements, whatever assists us in doing the basic movements, we cover under the internal state sensors. Whatever helps us in interacting with the environment, with environment, is basically looked as something that is external state sensor. The basic movements, of course, are position, velocity, and perhaps acceleration. What could be an interaction with the environment? Well, robot has to do a task which is to perhaps do some assembly task, which means there are forces which are going to come from environment. There are going to be movements from an environment, so torques and forces it has to be able to apply, it has to be able to withstand. Sometimes we are interested in knowing whether something is there or not. So then the issue of touch, or if what we are holding in our in the gripper, is it slipping or is it steady? So slip is another sensor which is important in robotics. Then there are various others. You can have range, how far something is. This is primarily important for mobile robots, where the robots are moving around in some environment, and how far is the obstacle is important to know. Then of course you can talk about full-fledged vision, interpreting what is ahead in the scene or what is around in the scene. And once again, if we come back to our analogy with the human beings, what are the internal state sensors do we have? Has anybody thought about what internal state sensors we have, or do we have any? Basically, if you want to see whether we have any internal state sensors or not, you can do one experiment. You can close your eyes and then you can move your arm randomly, and then keep your eyes closed and ask yourself, do you know where your arm is? And the answer would be yes, right? So there is something that it's apart from the visual feedback, apart from the fact that you may be integrating your position to see how much arm you have moved, but if you move randomly enough for long enough time, your integration will not be accurate, because the initial conditions and it won't be able to, there will be errors along the way. But still, even after a long random movement, you will be able to say where your hand is, what is the general orientation. You will be able to feel the velocity without having to look at it. So there are internal state sensors, and they are actually embedded. So we do have internal state sensors. Of course, we have the external state sensors. We are all very keenly aware of that. Our vision, our sense of taste, touch, smell, all these are external state sensors which make us behave in a very intelligent fashion and interact with our environment. So let us begin to look at internal state sensors. Okay, internal state sensors, if you refer to the diagram here, I have basically drawn a typical a couple of degrees of freedom of a typical robot arm. What you see is one link here which is got a revolute joint with respect to the link here, and then you also have one little link at the end. Maybe the end effector would be connected to that. Apparently there is a degree of freedom of motion about a vertical axis here and a vertical axis here, and then perhaps there is rotation about this axis here, right? So you have different motions are there. Now if you were using stepper motors to drive these joints, it's quite possible that you don't require sensing, that you can say you started out from a home position and then you have moved 100 steps, each amounting to, let's say, 0.9 degrees, then you know that you have moved 90 degrees. On the other hand, if the robot is interacting with the environment, there is force of gravity acting or there are external forces acting, then one cannot always be sure whether the 100 steps actually corresponded to 90 degrees or not. So in that case, it will be good to know where the robot actually is, and for that you will require some kind of sensing to be done. And so you will have typically things like position sensors, you may also have some kind of velocity sensor, and there can be different type of position sensors and velocity sensors. Obviously, in real robot, you will have to worry about all the signals coming out from these sensors and coming through wherever, the routing of these to the controller. And this actually in practical robot design this becomes a something to really worry about, how the cables are going to run and they will not interfere with the movement, they will not get entangled, they will not get damaged. So those are of course issues of practical robot design. We are not going to worry about that too much. Basically what we are saying is that if you have a controller, so let us depict this controller as a block here. What the controller does is actually going to look at what is desired, and that I am depicting by arrow here. This is the desired position, let's say, because the task typically would be that we will want to take the robot from one position in space to another position in space. And when we want to do that, we have the corresponding angles of the joints which correspond to the first state, and then we need to transform them into the second state, which will be a second set of joint angles or positions. Now at any time, so then the controller will generate, or something will tell the controller that this is the desired position, and from the desired position the actual position has to be compared, and that I am showing in this block here with a plus and a minus sign, showing that this is the actual, say, position or measured position. So if we take the desired position and the actual position, then we come out with what can be called error. And the controller primarily works on the error. Primarily, it can take other signals. In fact, it can look at the desired position, it can look at the next desired position to do something more intelligent. But at a very, very elementary level, what the controller will do is will look at the desired position, it will look at the actual position, look at the error, and then if the error is there, if it's large enough, then it's going to take some action which is going to be depicted as a amplifier. So the error is amplified so that it can actually drive some kind of a motor or basically the robot system. So this is representing the dynamics of robot. Now sensors come here because this is the actual response of the robot here. We take this and we measure it using sensors. And this is the signal that goes as our measured signal for whatever variable we are trying to control. So if it's position, then this will be a position sensor. If it's a velocity that you're trying to control, because there are tasks in which you will require to control the velocity. One example of that would be if you had a conveyor on which some part was going, and then you wanted to take the robot and pick up the part from a moving conveyor. In that case, you will have to choose a trajectory which will come to the part, align with it, then move along it, and then pick it up as it's moving along. So the velocity control becomes very important. So this is the kind of loop that we are talking about. This is basically a closed loop system. And closed loop system has the advantage that if there are external forces which are disturbing the motion of the robot, which are always there, then it can make corrections and not depend on what the original command we have given for motion. As in the case of the stepper motor driven robot, in which you don't have if you don't have any feedback, then you can say go 100 steps, but 100 steps may actually be 98 steps because something obstructed it, but we have no way of knowing because we don't have sensors. So sensors are very, very important in making robot do useful and accurate motions. Okay, so let's look at some of the sensors. Let's start with position. we will look at couple of sensors which are used for sensing position. The first one that you would all be familiar with is what is called a potentiometer. It is also referred as a pot in short. This is something that you would have come across in physics laboratory, for example, or you would have known it anyway. And basically it consists of a moving arm. If you are trying to measure, let's say, rotation of a shaft, then this arm would be mounted on a shaft, okay, and there is a resistor of some sort laid out along a circular path. Okay, I'm going to draw some terminals at the end of these, and this moving arm is connected through a wire which is flexible to another terminal of the potentiometer. So you get the idea that if the shaft moves, the arm will rotate. The arm is expected to be in contact with the resistor that has been laid out in the circular path. So if you attach some power source here, let's say we attach some V supply here, and we ground this terminal, then depending on where this moving arm is, let me color this moving arm as black here so that it's visible, where this moving arm is with respect to the zero potential point. So let's say we draw one line here representing where the minimum of the, where you have the moving slider contacting at the zero potential point, and then you have the actual position of the, so this angle here we call this theta, and we look at what is the maximum position it can reach is somewhere here, and that angle if we call theta max, then we have a relationship which is going to be talking about the position of the shaft with respect to the position of the wiper, which would be known in terms of the position on the resistor, because the resistance is assumed to be a linear resistance, which means resistance will keep on increasing with respect to this point as you travel around this resistor. So let me shade this also, because now my angles have cluttered up the picture. So this is the resistor film. This resistor can basically be a wound wire. You take a fine wire and you wind it about in a coil, and then you make sure the top surface is, the insulation is removed, so that when the wiper moves on it, you can get the resistor, you can have the flow of electric current taking place here. So wound wire type of they will give accuracies or linearity of 3 to 5% of full scale. This is the linearity figure. Now 3 to 5%, if you talk about the full scale, supposing the motion of the arm is 200 degrees of some joint, then 5% is quite a lot. It's 10 degrees. It's quite unacceptable. So one has to get better potentiometers, and conductive polymer type these are much better. They can give you fraction of a percent, so less than 1% of full scale. So there we are coming down to a couple of degrees or a degree of in terms of linearity. There is also the problem of noise because there is a moving contact, and although the noise problem is much reduced in the conductive polymer type, it has some kind of a damped response on that compared to the wire wound. Wire wound of course also has discretization because you go from one coil to another coil, one winding to another winding, so there is a discrete change in resistance that takes place, whereas the conductive polymer can give you a more smooth type of variation in resistance. Obviously the analog output is analog here, so if this is my V out, so we need, if we have a computer system which is going to be in the controller, then this may have to be converted into digital type of signal or value, and that there are devices available for doing that, called A to D converters. Now V out obviously is equal to theta divided by theta max times Vs. This is by simple resistance divider, voltage divider, and this can be written as some k times theta, because if Vs is a constant, theta max is a constant, then you have this is a proportional signal to the position. We can also write this as x times Vs, where x is the fraction theta over theta max. So depending on how far it's traveled along the resistor, you can have the voltage directly dependent on that. So basically the effective circuit that we have here is, you have a voltage divider circuit with, if the total resistance of the film here is R potentiometer Rp, then I have 1 minus x times Rp here and x times Rp here, and then I am taking the output from here, and typically when I am trying to measure the output, I will have to attach some equipment to it. It will have some effective loading resistance that will come in here. So in practice I will also have another resistance here, which is the, let me call that the load resistance, and this is what I am going to actually measure, and this, let's say, is VL. So in using a potentiometer, I can write down what my VL over Vs is. This is the, I'm trying to divide the voltage across this whole resistance, the whole resistance being 1 minus x times Rp plus the parallel combination of x times Rp and RL. So that is nothing but x times Rp RL divided by x Rp plus RL, and in the numerator you will have this part, which is the parallel combination, which is x times Rp times RL divided by x times Rp plus RL. So this is what we will actually measure, and if you say that there is some error compared to the ideal situation where you have, if you have RL approaching infinity, then you will see that this will approach the output resistance, output voltage that we have talked about here. Okay. Otherwise you can say that the error is some x times Vs minus VL. So we can calculate that out, and it turns out to be x times Vs times Rp divided by RL times x minus x squared. So this is the error, assuming that RL is much larger than Rp, which is the case. Typically the resistance of the potentiometer would be of the order of 100 ohms, 200 ohms, 500 ohms, whereas the load resistance that we are talking about will be of the order of kilo ohms. So maybe 10 kilo ohms would be a good number to think of, and that will give you some error which will be of the order of a fraction of a percent, right. So one has to worry about this loading aspect. Of course by using operational amplifiers one can minimize this type of loading effect. Okay, let's now look at another type of position sensor called optical encoder. Optical encoders are useful because they don't have any contact. In the potentiometer you had a film resistance and you have a wiper, and that creates problems of noise. In an optical encoder, on the other hand, we have a disk which is coded. So we have a situation where you have a round disk, and on the disk what we are doing is we are placing some diodes which will emit light, and we are putting some sensors. So let me put, let's say this is corresponding to the some 3 sensors here. On the other side, which is not seen, we have the source of light, and this is the shaft whose angle we are trying to measure. So what we're going to have is we're going to have some kind of coding on this disk. This disk may be opaque, and the coded parts may be transparent, meaning there may be holes in that, or the disk may be clear and you have some opaque sections of that. And as the disk rotates, because there is a light source on the other side and there are light sensors on this side, it will see some pattern of output. Okay, so photo detectors here. So let me write down photo detectors, and on this side we have LEDs. LEDs are sources of light, and so by looking at the pattern one can find out what the position is. This is the basic idea behind a optical encoder. And as I said, the good thing is there is no contact. This here, there is a air gap here, so there is no problem. It doesn't lead to any kind of electrical disturbances. Now this could be in the rotary variety, or it could be in the linear variety. In the linear variety you will have a coded linear segment, and you will have sensors mounted on that in the same kind of and then you will have some pattern on the linear encoder. So this is the rotary type, is the linear type. In robotics mostly we are dealing with rotary joints, although there are some linear joints, but linear encoders are more used in machine tools, NC type of machine tools. Here we are going to primarily concentrate on rotary type, but the principle is the same, and in fact we could think about the linear one because it's easier to draw, and the concept is the same, so we can illustrate with that. So what I'd like to do is I'd like to show you that if I have, say, different bands here of information. So I have shown here 1, 2, 3 for example. You can have more. Supposing I have 4 bands in which the pattern is something of this sort. So let me draw the 4 bands. So one combination is that all of them are transparent. Okay, let's say that amounts to 0 output. So I will have 0, 0, 0, 0 as the combination. Then I say next combination is where one of them is opaque, so then that will give us a corresponding output of 0001. And likewise I can put different patterns Okay, so the pattern I'm putting is a binary pattern here. Many of you may be familiar with this type of a pattern. Okay, what is going to happen next? You have this bit and you have this bit, and then you have all three of these. Notice that they are all unique patterns or combinations, and here onwards this will always be 1. And then you have here you have this one blackened, this one blackened, these two blackened. Then we have this one blackened. Then you have this along with this. You have this along with that, and then you have all of them black. Okay, so these are basically combinations 0 0 1 0, 0 0 1 1, 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1, 1 0 0 0, 1 0 0 1, 1 0 1 0, 1 0 1 1. Am I shifting? Yeah, 1 1 0 0, 1 1 0 1, 1 1 1 0, and 1 1 1 1. So you recognize that this is nothing but binary counting. And these are corresponding to 16 different combinations. And so on and so forth, 15 and 16. Okay. So if we have 4 bands, then we can do 2 to the power 4 times 2 to the power 4 the different combination, unique combinations which are possible. And therefore, if I have a disk which has got 4 such bands, I can distinguish between 16 different positions. Okay, this is basically called a absolute encoder. It's absolute because it doesn't depend on what the position earlier was. You can have a power failure and you turn on the machine again. As soon as the machine sees this pattern, it knows exactly what the shaft position is within the accuracy of that 16 divisions. So 16 of course is very crude figure. You need to have much higher resolutions. So if you try to have 8 bands, then you will have 256 possible positions, and if the that will give you something little better than 1 degree or worse than 1 degree resolution. That is not very good also. Yes, you have a question? Band meaning, see, I am having patterns of zeros or ones on the encoder disk. So it depends on how many of these photodetectors I have. So if what I have shown here is 3 photodetectors, so this disk will be able to detect 8 different positions of the disk. But if I have 4 of them, then I have 16 such possibilities. If I have 10 of them, then I have 1024 different possibilities of the position of this rotary disk. Right? Each band is, you take this what I have drawn here and put it in a circle. I have not drawn that because it is harder to draw in a circle, so I have drawn in a straight patch. So it is corresponding to the linear encoder. But the same thing, if you turn it around and join this edge with this edge, and of course because these will be concentric circles, the diameter of this will be smaller than diameter of that, or you will put the other way around. In fact, let this be on the outer side of the edge, so that you have finer divisions here, but you have larger linear distance available on the rim. So you can have more divisions there. That is the way it will be done. So is that clear now? Okay. So basically you will require at least 10 such bands. okay, to give you about 1000 divisions of a rotation, which will give you better than 1/3 of a degree of resolution. There is one problem though with this type of pattern that I have shown you, and that is that supposing I happen to read the encoder at say this instant, okay, or better if I try to read this at this instant, what is happening is I have, if this is 0, 1, 2, 3, then my bit 0 was 1, bit 1 was 1, and bit 2 and 3 were 0. Now in the next instance, as the rotation is taking place, the bit pattern is changing to 0, 1, 0, 0. So basically 3 of the bits are changing at the same instant of time. And what is, if I just happen to read it at this transition, then I will not be sure what the value I will get. I may get 0, I may get 1, I may get 2, I may get 4, any of these I can get depending on exactly how the timing, the precision of this particular edge is, which cannot be predicted. So this is a flaw in this type of a binary pattern, which can be overcome. It can be overcome by something that is called a gray encoding, and in the gray encoding, if I look at the same 4 bands, now the patterns will be different, but there will still be unique combinations of 4 bits. So here are my 16 boxes along each of the track, and I start filling out. First one is all blanks corresponding to 0. This is okay, there is no problem. Then instead of simply having this on like I had in the binary pattern, where I am allowing 2 bits to change at the same time, this has to turn off and this has to come on, and therefore we will not know what will happen. Maybe both will turn on first before the other one gets turned off, and that will give us a wrong value altogether. So we don't allow this to turn off yet. So we leave that on. We turn this one also, meaning make it opaque or whatever. Then in the next one we remove this first one, so that we have a unique combination here. So long we have covered these 2 bits, we have 4 different combinations, but they are in the different order, right? But we have the same, you can correspond different rows of this to different rows of that, so all of them are unique, but we will still call this 1, 2, 3, 4. So our code for 3 is now okay, it's not 3 as actually, because we are starting from 0, 0 to 15 as the 16 combinations. So basically we have 0, 0, 0, 1, 0, 0, 1, 1, and 0, 1, 0, 0, 1, 0. So there is a slight change in the pattern that I have done here. So how will I continue to generate this pattern? Well, I will take this on and I'll turn this one on now, because I couldn't have turned that off, because I want to make only one transition at a time, right? So I leave that on and I turn this one on, and then I will take these 3 I can do it, yes, I will turn this one on and this one on, okay. Then I will take this one on, this one is on, and I'll turn the middle one off, okay. Then the next one would be, so the way I generate the pattern, let me tell you the secret of that I have every 2 I am alternating here. So I could simply generate it blindly. So every 2 will be black and every 2 will be white. Here every 4 will be black and every 4 will be white. So I've got 1, 2, 3, 4. I leave 1, 2, 3, 4 blank, and then I have the next 4, right. Then I take every 8 of these, so I have got 1 2 3 4 5 6 7 8, and here I'll take every 16 starting from 8 position, 1 2 3 4 5 6 7 8, and 9th onwards I have got this is all black. Okay, you will notice that what I have done here is, if you look at any pair of combinations next to each other, you will see that there is only one bit that changes. So let us just look at that. So I have 0 1 1 0, then I have 0 1 1 1, then I have 0 1 0 1, then I have 0 1 0 0, then I have 1 1 0 0, 1 1 0 1, 1 1 1 1, 1 1 1 0, 1 0 1 0, 1 0 1 1, 1 0 0 1, and 1 0 0 0. So pattern is different, but they are all unique, and therefore if I am able to correctly interpret this combination, then I can get the position correctly, and I don't have the problem of transitions, because in any transition if I look at, there is only one bit is changing, so either that bit would have changed or it would not have changed. The error would not be there. There would be no spurious readings coming in between, and that is very important. So obviously this is not so intuitive, because most people will be able to say something about binary code, but gray code is something that is a little difficult to get used to. So of course you can build an electronic circuit which will convert your gray bits into binary bits, and then you can display that. So that is very simple. You take your gray bit 3, gray bit 2, gray bit 1, and gray bit 0, and here I have binary 3, binary 2, binary 1, and binary 0, and you will notice that there is no difference in the most significant bit. So I connect this together. This is my MSB, or most significant bit. Then for getting the next one, I need to use a XOR gate. So I connect this to an XOR gate and get my B2. Does everyone know what a XOR gate is? It's basically a logic device. You know what AND operation means. When two inputs are there, both are on, then the output is on. Otherwise any other combination, it is not on. Similarly OR is when either of the two inputs are on, then the output would be on. In a XOR, it's similar to OR except one combination, that is when both the inputs are on, the output remains off. So it has to be strictly one of them, not both. So if you have a device like that, that can be used to convert your binary to gray level to binary, and of course vice versa also, with a little difference. So one can easily build this kind of circuit in the hardware and attach it to the encoder, which has got gray level inside. Inside you will always like to have gray level. Output you can give a option of having either gray output or binary output. Okay, so these are absolute encoders that we have talked about. Absolute encoders, as you see, if you want to improve the resolution of it, then the number of bands keep on increasing. Then creating that disk which is going to have 12 bands or 10 bands becomes an expensive process, and that drives up the cost of the encoder. Also there will be so many more photodetectors, and all the alignments and everything is crucial. So the cost of these are much higher than cost of another variety of encoders, which we call incremental encoders. The basic idea in an incremental encoder is that we do have different tracks of pattern, and different tracks of pattern, let me draw them for you here. Once again, we will have some sensors, so I am putting some space for the sensors. I am covering the track. And these are going to be divided in opaque and transparent sections, parts. So here is my opaque parts alternating with the transparent parts, and part of it is hidden under the sensor, this thing, and then of course we have. Now we are not going to have multiple bands, we will only have 2 bands here. Okay, the second band is going to have the same pattern but displaced by 1/4 of the cycle. So in the middle of the black and the white, these are etched out. This will go up to here, so this will be black here, and then of course the next black will start there, whatever. So we will call it channel A and channel B. In some cases you will have a third channel also, but the third channel will only have one spot. It's called the index channel. Okay, the idea basically is similar. You have light source on one side and photodetectors on the other side. So assuming that the light source is at the bottom, I have 3 photodetectors here, and then this whole thing is mounted on whatever is moving. So this is moving back and forth, whereas this is fixed, right? So what is the kind of output I expect to see in the photodetectors? Well, basically if I assume that the photodetectors are very small compared to the bandwidth here, then either the photodetector will get light or it will not get light. And if it's getting light, then let's say it's 1 or a 0 or whatever, so we'll get a pattern which is going to be basically a square wave type of pattern. Okay, so let's say this is channel A. Channel B is going to depend with relation to channel A, is going to be quarter cycle behind, because if it's moving to the right, okay, so if it's moving to the right, this black will come first, assuming this is 1, because that's what we've been assuming in the earlier this thing. So this is corresponding to 1 and this is corresponding to 0, let's say. So this black will come in first, then quarter cycle later this black will come if I am moving to the right. So then my pattern would be quarter cycle behind. Lag. This is channel B, this channel A, and this is for rightward movement. Okay, moving right. On the other hand, if I was moving left, you can see that what will happen is you will have this leading, because now the roles are reversed. This part will come first, then this part will come if I am moving to the left. So then our B channel will look different, and B channel will look something like this. This is quarter cycle lead moving left, right. So if you have to see that I am talking in relation to this leading edge, let us say. So at this time, this I have upward transition here in channel A. In channel B it is not yet come, little later in time it will come, that is why I am calling it a lag, and here it is already come, quarter cycle before. So this distinguishes, this can tell me what is the direction of motion, right, from whether to look which way the lag is, I will be able to determine what is the direction of motion. Now to know the position, what I have to do is to simply count these. If I count these number of pulses coming from here, then I will be able to say how many pulse worth of rotation or motion I have had. This can be in a circle. I have shown this in linear band because it is easier to draw again, but it can be in circle, and then I can again have a pattern which matches, will give the same type of output, and I will be able to say what is the position from the beginning, from some reference position. Now this is the problem you can say with this encoder compared to the absolute encoder, that is that you have to know what is the initial position that you started out from. An initial position, once you know that, then you can count up or down depending on whether you are moving leftwards or rightwards. And this is the function of the index pulse that is provided. It helps you to determine where the encoder is in the beginning, right. So there is a procedure that you will have to go through whereby you will move this encoder, assuming that this encoder rotates only once. Let us assume that or it moves only this motion. In the rotary one you can have multiple rotations possible. So in a rotary one, if you have an index pulse, you don't know whether after 20 rotations you got the index pulse or after 2 rotations you got the index pulse. So in a rotary one, you will require some assistance from some other device or some other sensor to determine where your initial position was when you powered up. There are standard procedures for doing that. You may use a potentiometer as a approximate measurement device to bring it to some known position, and around that you will move slowly until the index pulse comes, so you know precisely where you are then, right. Or you may take it to a home position, extreme position, and then start moving and say, okay, this is my third time the index pulse has come and this corresponds to 20 degrees, whatever the case may be, but one can do that. So it requires that initial determination of position. So this is one of the problems. The other thing is, so here we if power is on, we don't know where it is, okay, initial position not known, uncertain. It requires some other type of information to be able to find where the position is. Other problem is that it requires more processing. Right. In the case of absolute encoder, you just read that photodiodes, and if they, depending on what the pattern was, you immediately know where you were. Here you have to do some processing like counting. You have to determine the direction, you have to see which way you are moving and keep track of where you are, okay. But these are of course much less expensive. Because they are such much simpler construction. You only have 2 tracks, and those 2 tracks are enough for you to determine the position. So we will look a little more about how this is accomplished actually in terms of the processing of the signals which you are getting in channel A and channel B, and how we can determine the position from that we will see in the next class. Thank you.